So if we replace in D hydraulic equal 4 times area over P wet, if we replace the cross-sectional area by its expression and the wet perimeter by its expression, then we can simplify D hydraulic. Pi over pi will cancel out. D out plus dn over D out plus dn will cancel out. So we can deduce that for an annulus, we can calculate the hydraulic diameter as the difference between the outer diameter and the inner diameter. So if you want, whenever you have a surface different than a circle, and you want to calculate the Reynolds number, you can replace D, okay, by the hydraulic diameter. And Reynolds number can be evaluated as rho times velocity times D hydraulic over mu, okay? So this is for the Reynolds number. Now, how to calculate velocity, the mean velocity in the annulus? We know that the mean velocity in the annulus is equal to the mass flow rate m dot. So here m dot oil, which is given, over rho A. Because what is the formula for m dot? The mass flow rate is equal to rho times the mean velocity times the cross-sectional area of the annulus, okay? So here we have already determined the cross-sectional area of the annulus. The cross-sectional area of the annulus is pi d outer square minus pi d inner square over 4. This is the cross-sectional area, okay? So now I can replace in this equation the velocity by m dot over rho A. Okay, and when I multiply by rho d hydraulic over mu, rho will cancel out. And I can also simplify, because here you can write instead of d outer square minus d inner square, you can write d out minus dn times d out plus dn. So you can simplify d out minus dn from both sides. And you end up with the following expression for Reynolds number. So the Reynolds number for an annulus can be calculated from 4 m dot times pi d out plus dn times mu. So if you replace, you get the value of your Reynolds number. And here, since the flow of oil is outside of my tube, you know, this is my inner tube. I have convection from the inner side HN, and I have convection from the outer side H out. So relative to this surface here, relative to the surface of the tube where heat transfer is taking place, oil is from the outer side, okay? So it's an external, we say it's an external flow. Oil is external to this surface. And this is why, in order to get the convective coefficient H, we need to search for Nusselt number, not for flow inside the duct, for flow outside of a duct. Okay? So you have two types of flow, of forced flow, internal and external. Here, the flow inside the tube is internal to this tube, but the flow, but oil is from the outer side, it's flowing over the tube. So we say it's an external flow, okay? So now if you go back to your appendix, you have Nusselt relation for flow inside a tube, so for internal flows, and you have other relations for Nusselt, for fluid that are moving over the tube or external flow. Let us go and search for these formulas. So if we consider again our appendix, we need to move down to search for external flows formulas. So here we are still laminar flow inside in a circular tube or in a tube with annulus form. We don't want this. Let me check if we have them here. If not, I will post them for you, okay? Okay, so here in this appendix, we just have uh, formulas for flow in a circular annulus with a surface insulated. So here in this appendix, we didn't put the relations for flow from external side. I will update it for you. I will add the equations for external flows, okay? But it's the same method. And all you have to do is to go to the appendix and search for relations at the external side. Or if you want here, look, it's true that oil is external to this surface, okay? But it's if you consider the circular tube. But if you consider the annulus, okay, oil is inside the annulus surface. So you can find, you can go to your appendix of inner flows and try to search for the case of convective coefficient for a flow over an annulus, okay? So here you can say that if we go to our table, to our appendix, we can search for flow inside annulus geometries. Okay, so let us go back and try to see if we have formulas for flow in annulus. Okay. Let us go back to our tables. Okay, look, here you have the first table that we used together is for flow in a circular tube. Okay, and this doesn't apply for oil. For oil, it's flowing over the inner tube, but it's flowing inside an annulus area. Okay, so we can search for a table that is giving us information about flow in annulus. This is the table. So table 8.2 is giving us Nusselt number for fully developed laminar flow in a circular tube annulus with one surface insulated and the other at constant temperature, which is our case here because look, oil is flowing over the circular tube, but it's flowing inside the annulus. So because it's flowing inside the annulus, we can apply formulas of inner flow through annulus geometry. Now, what is the information required? We need to calculate the Reynolds number. We calculated the Reynolds number and it was really small. It is much smaller than if you want the limit of turbulence. So from our Reynolds calculation for the oil, we can deduce that the flow in the annulus is laminar. So this table can be used because this table is specific for laminar flows. Since the laminar condition is satisfied because we got a low Reynolds number, then we can use this table. But we have other conditions to make sure that we can use this table. The conditions are that we have one surface insulated, and here because it's a heat exchanger, at the outer side, we have good insulation, while for the inner side, okay, we have the temperature of the surface, which is imposed. So here we have T surface, okay? So since these conditions are satisfied, we are imposing a temperature at the surface here, and we have insulation from the other side, we can use this equation, okay, this table. Now, as you can see here, they are giving us two Nusselt numbers. One for Nusselt with the inner surface, and Nusselt for the outer surface. But in our case, since insulation is from the outer side, then Nusselt of interest will be for the inner surface, because we have convection with the inner surface in this case, since the outer surface is insulated. If you have the opposite, if the inner surface is insulated and the outer surface is exposed to a certain heat transfer, then you get Nusselt out. But here, you are interested in convection with the circular tube, so you need to determine what is Nusselt from the inner side, okay? And to get Nusselt from the inner side, you need to consider the value of, all you have to do is to find what is dn over d out, okay? So here in this problem, dn is the diameter of the inner tube, and d out is the diameter of the outer tube, okay? So you need just to calculate the ratio dn over d out, and depending on the ratio that you obtain, you will select what is the formula to use, okay? Because here, depending on the ratio, the Nusselt will change. So here we have the out, we have the n. We calculate the n over the out to select the appropriate Nusselt. Let us go back to see what is the out and the n. So first, as you can see here, Reynolds was really small. Yani it's of order of 100, while Reynolds of turbulent is of order of thousands. So since this is a small value, it's a laminar flow. And then if we calculate in this problem dn over d out, we have the outer diameter is 0.045 meters. The inner diameter is 0.025. So the ratio is 25 over 45 equals to 0.56. So if we go back to our table, for a value of ratio equal to 0.56, we don't have 56 exactly, okay? So we can do linear interpolation like you do in thermodynamics. And you say, I need to get for 0.56, what is the value of Nusselt inner? Okay, so all I have to do is to interpolate between these two values. So I can write 0.56 minus 0.5 over 1 minus 0.5 equals to Nusselt inner that I want minus at 0.5, what is Nusselt? It's 5.74 over, for a value of dn over d out equal to 1, Nusselt number is 4.86. So 4.86 minus 5.74. So this equation will give me the value of the Nusselt number from the inner side at this surface, okay? And now, once I calculate my Nusselt number, which is around 5.63, I can calculate the value of H out. Now, please pay attention. Nusselt is H times characteristic length over K. For an annulus, the characteristic length is d hydraulic. For a circle, the characteristic length is the diameter of the circle. Okay, so now all I have to do is to say that H out is equal to Nusselt from inner side times K over the hydraulic diameter of the annulus, and we have proved together that the hydraulic diameter of the annulus is d out minus dn. So now we calculate H out. Once we have H out, we go back to our U value. The overall heat transfer coefficient is 1 over HI plus 1 over H out. And once you calculate U, now you are ready to find the length of your heat exchanger. Why? Because we said that Q is equal to the overall heat transfer coefficient times the area times delta T. And what is the area of exchange here in my heat exchanger? All heat transfer is taking place through the area of the inner tube. Yani my area here is pi d inner. And don't forget, what is delta T here? It is delta T logarithmic that we calculated at the beginning of the example. So over pi d inner. We have the value of Q. How we got Q? Q is m dot Cp delta T. You can calculate it for the hot fluid. You can calculate it for the cold fluid. It's equal because we assume no losses. So all heat lost by the hot fluid is equal to the heat gained by the cold fluid. Okay, so you have a Q, you have U value now. The area is pi d inner times the length. Your only unknown is the length. So you can say that the length L is Q over U times pi di times delta T logarithmic. And then you can find out what should be the length of your heat exchanger to ensure this, if you want. Hey, there's a total length of the duct, of the pipe, okay? And of course, 60 meters is high. So you can do like, you can turn it in this way. And you can have your pipe not straight, okay? You can put it in this way to ensure a total length of 65.9 meters. So we can, some remarks, the hot side convection coefficient controls the rate of heat transfer between the two fluids. Why? Because if you compare the convective coefficients between the inner and outer side, the outer side convective coefficient is really small, while for the inner side, it's much larger. For the inner side, you have H inner equal to 1,250 watt per meter square Kelvin, while for the outer side, it's just 38.8. So what is dominating the heat transfer is the convection, okay, from the hot side, from the inner side, okay? This is why the low value of H0 will explain having a large value of L, because you know, to enhance heat transfer, you need high convective coefficients. So in case the convection from oil side was high, this can help heat transfer, and this can lead to better values, okay, to lower values of L. And you don't need this very high lengths to achieve a heat transfer. That's why in general, okay, we try to, if you want, enhance convection as much as possible. So here, if we have a higher value for H out, this can enhance a lot the convective process and will reduce the value of N. But since HO was really small, okay, this resulted in a large value for the length of the heat exchanger. So how we can enhance, if you want, this heat transfer, we can do several enhancement methods. We can, if you want, use fins. We can increase the area of heat transfer. We can try to have larger velocities to increase the convective coefficient. So we have a lot of methods that can help into reducing the size of the heat exchanger. And now, since H inner is much larger than H outer, the tube wall temperature will follow closely that of the coolant water, because water is from the inner side. and the convection with water is much larger than the convection with oil. That's why the temperature of the surface will be very close to the temperature of water because of high convection with water. From here, we can assume the assumption of considering that the temperature of the surface is uniform is accurate because this surface will be affected mainly by the temperature of water because we have a high convection from the side of water. Any question on this before we continue? Okay. Now, in heat exchangers, we have several analysis methods. We have done together the first method of analysis using delta T logarithmic, okay? But this method is not always applicable. So the LMTD method, which is using delta T logarithmic of a heat exchanger analysis is simple and can be used when the fluid inlet temperatures are known and the outlet temperatures are specified or can be determined by energy balance expression. So if you have only one unknown temperature, you can use the logarithmic method because the energy balance will give you the unknown temperature, and you can use the methodology before with Q equal UA delta T logarithmic to find any unknown in the area, okay? But sometimes we don't have three temperatures. We have only two temperatures known and two temperatures that are unknown. In this case, we cannot use anymore the previous method. So we need to develop another method that can assess the effectiveness of a heat exchanger. This method is called the effectiveness NTU method. Let us discuss what is this method. So, however, if only the inlet temperatures are known, the use of LMTD method will require an iterative process and it will be a very long method. That's why it will be preferable to employ an alternative approach, which is the effectiveness NTU method. To be able to understand this method, first we should define some parameters. So to define the effectiveness of a heat exchanger, we must first determine the maximum possible heat transfer rate that can take place through the heat exchanger. And we will prove together now that the maximum possible heat exchange is C minimum times T hot N minus T cold N. Okay, what do we mean by this? First, what is big C? Big C is m dot times the specific heat. So it's m dot times C. And you know that in heat transfer between fluids, we can say that the heat transfer is m dot times specific heat C times delta T. Now, if we name m dot C big C, so we can replace this by big C. So Q is equal to big C delta T. Okay. Now, delta T can be, what is the maximum possible value of delta T? Delta T is the difference between the hot and cold temperatures, average temperatures. Okay. But we know that, and we have seen that in case of counter and parallel flow, it can be evaluated by delta. So by delta T is varying, okay, over the whole surface. And when we considered if you want a certain value for delta T, we did what? We did for, let's say, for the hot fluid, we did T hot in minus T hot out. In case we are considering the hot fluid, we do m dot Cp T hot in minus T hot out. In case we are considering the cold fluid, we say Q is m dot C T cold out minus T cold in, okay? But what is the maximum possible difference? You know that the lowest temperature is for T cold N. So the inlet temperature of the cold fluid is the minimum temperature that we can have. And the inlet temperature of the hot fluid is the maximum temperature that we can have. So T hot N is equal to T maximum. So we can say then that the maximum possible value of delta T, the maximum temperature difference between the hot and cold fluid, is T max minus T minimum. And since T maximum is T hot inlet and T minimum is T cold inlet, so we can say that delta T max, the maximum possible difference in temperature, is T hot inlet minus T cold inlet. Now, why we are multiplying by C minimum and not C maximum? What do we mean by this? You have a hot and cold fluid, okay? And for any of this fluid, the heat transfer can be written as big C times delta T, okay? So you can say that C cold times delta T cold equals to C hot times delta T hot. According to this energy balance, if one fluid is experiencing a larger value of delta T, it should be characterized by a smaller value of big C. Yani the fluid having the smallest C will undergo the largest temperature difference. So since here we are determining the maximum possible temperature difference, we should multiply it by the smallest value of C, because the fluid having the smallest value of C will undergo the largest value for delta T. From here, we defined the maximum possible heat transfer that can take place. It's C minimum times T hot N minus T cold N. Now, actually, in the actual case, the Q is smaller. From here, we can define the effectiveness. The effectiveness, okay, which is the ratio of the actual heat transfer that is taking place over the maximum possible heat transfer. And to calculate epsilon, we can do it in two ways, because the Q can be calculated or for the hot fluid, it's equal to big C hot times T hot N minus T hot out, or also, okay, we can calculate it from the cold fluid. So it depends what are the temperatures that we know. We decide if use the formula with hot temperatures or cold temperatures. So in case I know the temperatures of the cold fluid, so I can use that Q actual is C cold times T cold out minus T cold in. Okay? Now, how to determine C minimum? C minimum, I just have to compare C hot and C cold. And the smallest between them will be equal to C minimum. Okay, so this is how I can calculate the effectiveness of my heat exchanger. Epsilon is a dimensionless number and it can range from 0 to 1. This parameter is very useful, okay, because epsilon, T hot inlet and T cold inlet are known, but what are unknown are the outlet temperatures, okay? So we can say that in general, the inlet temperatures are known. So I know T hot N, I know T cold N. So if I know the effectiveness of my heat exchanger, if epsilon is given for me, I can deduce T cold out from this relation and T hot out from this relation. So knowing the effectiveness of my heat exchanger, I can get it from a catalog for my heat exchanger. Knowing epsilon, I can T hot and T cold in, I can calculate the outlet temperatures T hot out and T cold out. So this is the idea of defining an effectiveness for my heat exchanger. Now, how to get the effectiveness of my heat exchanger? As we said, we can determine it experimentally, and for each type of heat exchanger, you can have graphs to give you epsilon, or you can have tables, as we'll see together now. We'll see that the value of epsilon will depend mainly on two parameters. A parameter that we'll define now, which is called NTU, and another parameter related to the properties of the hot and cold fluid, and which is big C minimum over big C maximum. Yani we should do m dot times small c. We calculate it for the hot and cold fluid. Then we select the smallest one. We put it in the numerator, and the biggest one, we put it in the denominator. And we do the ratio C minimum over C max. So if we know C min over C max, and if we know the NTU, which is defined, which we'll define now, we can calculate or find epsilon. Now, what is the NTU? NTU is the number of transfer units. It's a dimensionless parameter that is widely used for heat exchanger analysis and is defined as follows. NTU is the U value, which is the overall heat transfer coefficient of the heat exchanger, times A, which is the heat transfer surface area of the heat exchanger, over C minimum. We can note that NTU is proportional to the area. Therefore, for specified value of U and C minimum, the value of NTU will be a measure of the heat transfer surface area. And therefore, the larger the NTU is, the larger the heat exchanger. Now, for example, as I told you, epsilon will be given for you or in empirical relations or in graphs. So, for example, a specific form of the effectiveness NTU relation for a parallel flow heat exchanger. So this also will be given for you in the exam in the appendix. In the appendix, they will give you for different types of heat exchangers what is the formula relating epsilon to NTU and C minimum over C max. According to this, if you know the NTU and C minimum over C max, you can calculate the value of epsilon. So the above equation applies for any parallel flow heat exchanger, irrespective of whether the minimum heat capacity rate is associated with hot or cold fluid. So if C minimum is C cold or C hot, it doesn't matter. As long as the heat exchanger is of parallel flow type, then you can apply this formula. And for different types of heat exchangers, you have different relations. So you determine first what is the type of your heat exchanger. And here, CR is, as we said, CR represents the ratio of C minimum over C maximum. It's the heat capacity ratio. And we are defining here for different types of heat exchangers, parallel flow, counter flow, shell and tube. We have defined together last time shell and tube and cross flow heat exchangers. And if you remember, we talked about possibility of single pass or several pass, okay? So all you have to do then is to determine the type of your heat exchanger. And according to this type, you can select what is, for example, if you have cross flow with both fluids unmixed, so this is the case when you have fins separating the outer flow, then you can use this formula to get the epsilon function of NTU and the specific heat ratio. Okay, so we deduce that depending on the type of heat exchanger and depending on C min over C max, the value of epsilon can change. And we go to the tables to select the appropriate relation that we need. Sometimes, okay, to calculate epsilon, you need NTU, and you need to know the area. So in case the area of your heat exchanger is known and you want to calculate for, let's say, temperatures, you can use the method epsilon function of NTU and A. On the other hand, sometimes it's the opposite. Sometimes we know epsilon and we need to find the area. So in this case, we need another, because as you can see, these equations are really complex. So here epsilon is defined function of CR and NTU. What if I know epsilon and I want to find the NTU? The functions here are really complex. That's why we need to define NTU function of epsilon. So in case I know epsilon, I will not need to use these formulas. I will need to use a formula in the following form. I need to use a formula in NTU equals a function of epsilon and C minimum over C max. So also here another table will give you the relations in the opposite case. Yani in case you know epsilon, epsilon is not unknown, and you know CR, and then you need to solve, for example, for your area, then you need to use the opposite way, the formula in the opposite way. You need to express NTU function of epsilon and CR. So here for different types also of heat exchangers, we are summarizing for you NTU function of epsilon and CR. And depending on the given, you will decide which formula to use. Okay. Now, as I told you, the relations can be given in empirical form, in tables, or graphically. And here you have graphs that will give you for each type of heat exchanger. For example, if I have a parallel flow heat exchanger, I have graphs for NTU, for epsilon function of NTU, for different values of C minimum over C maximum. So for example, if you calculate C min over C max and you got 0.5, and you know that the NTU is 3.5, you say, I will use the graph. I take NTU 3.5. It will intersect the curve of C min over C max 0.5 at this point. I can read the effectiveness. The graph can be used in both ways. And sometimes you know epsilon. If you know epsilon, for example, equal 0.5, and you know that C minimum over C max is 0.75, you say I will take the intersection with the curve of C min over C max equals 0.75, and I can read the value of NTU. So graphs are easier to use if you want, but they are not accurate as the functions. So it depends. In the exam, if they don't force you to use the table, you can use the graph. The graph is faster. Okay. So here we can see graphs for different types of heat exchanger. For example, here you have the effectiveness graph for a shell and tube heat exchanger with one shell and the multiples of two tube passes. So this is the figure of the heat exchanger. You have the shell and you have tubes, okay, that are inside the heat exchanger. So you can have the number, this is one tube, two passes. You can have several tubes.